So today we have the pleasure to have with us Ingebritsen from USGS in Menlo Park. He made his PhD in Stanford, and then after that he spent all his career in USGS. You probably know him perhaps from his book on groundwaters in geological processes. And today so he is here to be visiting the two Frédérics in the team Physique des sites naturels, and so he's playing with them, and next week they will go in Pêche-Merle, I think, to make some measurements. And so today we'll give a seminar on the Cascade volcano chain in the US, and specifically also giving some insights on very recent monitoring of one of these volcanoes in Lassen Park. Yeah, that's it. Thank you.
Thank you very much. I think I'm use these microphones, right? Okay. Well, as the director said, I'm going to talk about hydrothermal monitoring of active volcanoes in the United States, and it's a great pleasure to do so here at IPGP, which houses great expertise related to essentially every facet of the work I'll talk about today. And of course, IPGP also has the important responsibility of monitoring the 3 French volcanoes, as well as being engaged in volcano science worldwide. And I particularly like to thank my hosts, Frédéric Perrier and Frédéric Girault. And there are a lot of contributors to the work I'll talk about today, many USGS colleagues, plus folks at the University of Utah, the University of Western Washington, the National Park Service, and the U.S. Forest Service. And what I'm going to do is I'm going to start with a broad overview of hydrothermal discharge in the Cascade Range. Then I'm going to talk about our monitoring network. Then I'm going to talk about recent volcanic unrest in Northern California, and then some new research directions. And as most of you probably know, the Cascades are the only volcanic arc in our lower 48 states, and they span our northwestern states of Washington, Oregon, Northern California. They also extend on up into southern British Columbia. They're caused by subduction of the Juan de Fuca microplate under the North American plate. So first, an overview of hydrothermal heat discharge in the Cascades, including some comparison with other volcanic arcs. Back when we were designing the monitoring network, we did a careful inventory of the discharge of heat from 3 kinds of features, from fumaroles, steam vents, from thermal springs, and from these slightly thermal springs where temperatures raise just a few degrees above ambient. And here's what the hydrothermal heat discharge look like when they're plotted as cumulative functions from the Canadian border on south to about latitude 40 in Northern California. Discharged by fumaroles, by thermal springs, and by these slightly thermal springs, a total of about 1,100 megawatts by all 3 modes over an arc length of about 1,000 kilometers. And the heat discharge by slightly thermal springs actually turns out to be the largest mode of hydrothermal heat discharge in the Cascades. And these steps show you that there's relatively concentrated heat output here in northern Oregon, and again, in Northern California, especially in the Lassen region. So how does this hydrothermal heat discharge in the Cascades compare with other well-studied volcanic arcs? Well, basically, hydrothermal discharge in the Cascades seems to be comparatively weak. The hydrothermal output in Japan is about 2.3 megawatts per kilometer of arc length, excluding any slightly thermal springs, which the Japanese haven't inventoried. And the comparable number for the Cascades, excluding slightly thermal springs, is only 0.4 megawatts per kilometer. And the comparable number for the Taupo volcanic zone is about 28 megawatts per kilometer, so nearly a 2 order of magnitude range here. And I think each of these individual numbers is fairly well constrained, probably better than plus or minus 50%, which really isn't so much when you're talking about a 2 order of magnitude range of variation. You can compare also these values from the Apennines. This is an inventory that did include slightly thermal springs in a well-mapped part of the mid-ocean ridge. So The hydrothermal heat output from the Cascades is modest by global standards. However, even though it's modest relative to other volcanic arcs, the current hydrothermal heat output from the Cascades, again about 1 megawatt per kilometer, is about 10 times larger than the average quaternary volcanic heat output. And in fact, if you do a heat budget, you'll find that the hydrothermal heat output may be comparable to the heat supplied by magma intrusion. So if you think about the various ways that heat can be transported from the land to the land surface, conduction, volcanic eruption, various forms of hydrothermal discharge, the hydrothermal discharge is by far the largest. So it's very important to the overall heat budget of the arc, and that's the case for other more vigorous arcs as well. Now these curves represent quasi-steady hydrothermal heat discharge, and there were large hydrothermal transients in the past century associated with volcanic unrest at Mount Baker and at Mount St. Helens. And for these we have sort of before, during, and after values of hydrothermal discharge. At Mount Baker, for instance, hydrothermal discharge increased from about 10 megawatts in the early 70s to about 75 megawatts in 1975, and now it's back around 10 megawatts again. So that's just a little bit of context with respect to hydrothermal phenomena in the Cascades and Cascades relative to other arcs. So now on to our hydrothermal monitoring network. And first, the motivation and methods. And with respect to the broad motivation, I usually ask U.S. audiences, how many eruptions do you think we've had in U.S. territory since Mount St. Helens in 1980? And from how many different volcanoes? And it's usually more than most people think. So the broad motivation of our work is to reduce exposure to and damage from volcanic hazards. And the United States is thought to have about 170 young volcanoes capable of erupting, and since 1980, 44, and we use 1980 as sort of a benchmark, because that was Mount St. Helens, and that's when we started making a concerted effort at volcano monitoring. From 1980 to 2015, 44 different U.S. volcanoes produced 115 eruptions and 51 episodes of notable volcanic unrest. And the point of this slide, this inset here, is that most of our active volcanoes are on what we call public lands, which are very extensive in the western United States. These are lands that are held for the general public, and they're managed by federal agencies. And just to give you a sense of this, about 90% of the state of Nevada is public land. About half of California is public land. Nevada and California together are about a little larger than France, and about 2/3 of that combined land area is public land. So the land management agencies are important partners for us in this work. And by land management agencies, I mean the National Park Service, the U.S. Forest Service, and the U.S. Fish and Wildlife Service. And in the Cascades, all the major volcanoes are on public lands. And then finally, I want to emphasize this point, that because of improved instrumentation, the ratio of known non-eruptive unrest episodes to actual eruptions is fast increasing. We're just seeing things that we wouldn't even have noticed 20 or 30 years ago. So that's the motivation in very broad terms. Well, why hydrothermal monitoring in particular? Well, there's some evidence in the literature that time variation in hydrothermal phenomena can yield useful diagnostic information. However, historically, most of our measurement and sampling of hydrothermal features has been done sort of campaign style on a very intermittent basis. And the intermittent data aren't well suited for comparison to the continuous seismic and geodetic observations. They're sort of the backbone of volcano monitoring. So our goals were to generate continuous data streams to permit comparison with other geophysical data streams, to better understand the degree of natural variability during quiescent periods, develop baseline data for key sites that we could reoccupy during unrest. And then a motivation specific to the Cascades was the spectacular water chemistry anomaly at South Sister in Central Oregon, which essentially coincides with a bulge mapped using INSAR in the early 2000s. And here the red color is the sulfate to chloride ratio in springs, and the blue is chloride concentration in springs, and the chloride concentrations go up to about 40 times background, as do the sulfate to chloride ratios. And the sulfate, chloride, and helium isotope anomalies all essentially coincide with this bulge. Now the problem here was that our first detailed geochemical data were from late summer 1998, which is about when the bulge started. We have very little pre-bulge data. All we really know is that there was already a chloride anomaly here in Lower Separation Creek below the bulge. I doubt that, does anybody here remember this bulge? It was a long time ago now. It was news in the western U.S. at the time because these volcanoes are called the Three Sisters, and there was a lot of talk about the growth of a west sister and a fourth sister. And we worked with a wilderness ranger who told us that this is deep in the wilderness, a long hike or horseback ride and multi-day. He said that his rangers always hated going back in there, but the extra 10 centimeters of elevation was really killing them. So if we could choose a single hydrothermal parameter to sample continuously, it would probably be the helium isotope ratio. That's something I'll get back to later on, but we don't yet have the technology to do that. And for the non-volcano folks, I should probably say a little bit about helium isotopes and their implications. Helium-4 is generated by radiogenic decay in the crust, as most of you know. Helium-3 is thought of as primordial or mantle helium and or magmatic helium. And we think that an increase in the helium-3 to helium-4 ratio may be the single best diagnostic we have of the influx of new magma to a system. But we can't continuously sample helium isotope composition yet. This gas sampling in the Three Sisters region did reveal a strong correlation between helium-3 concentration and chloride concentration. And chloride concentration fluxes are something that, of course, we can monitor continuously. And in fact, the data from South Sister showed strong intercorrelations between helium-3 concentrations, chloride concentrations, and heat in the spring group. So all three coming from a common and presumably magmatic source. And in addition to Three Sisters in the Cascades, there's also an anecdotal report by a reputable observer that Lewitt Springs temperature and discharge increased prior to the renewal of the Mount St. Helens eruption in 2004. And I say reputable because this gentleman is actually the head of the USGS Volcano Disaster Assistance Program. But, you know, the information is nonetheless anecdotal. There weren't any measurements, and it's usually not till after the event that we come in and make systematic measurements. So our motivation for experimenting with hydrothermal monitoring stems in part from what we see in hindsight as missed opportunities. And the USGS does have a strategic plan for improved monitoring of the nation's volcanoes, and it's called the National Volcanic Early Warning System, or NVEWS. And when we selected sites for hydrothermal monitoring, we first did a pretty careful inventory of hydrothermal features at the top 12 Cascade volcanoes per the the NVEWS threat rating. The 12 volcanoes judged to be highest risk. And full implementation of NVEWS is supposed to include hydrothermal monitoring. So we wanted to experiment with how to do such monitoring. So we selected 25 sites associated with 10 of those 12 volcanoes. And all these sites already have some indication of magmatic influence, elevated helium-3 to 4 ratios, large fluxes of magmatic CO2, large heat fluxes, often all of the above. And our fumarole sites basically consists of thermistor nets. Each thermistor records hourly values coupled with annual gas sampling. Only once a year, in part because a lot of these sites at volcano summits are fairly hard to get to. And these are schematics of our thermistor nets at Mount Hood and at Medicine Lake in Northern California. And this is part of our Mount Hood site, I think you can see, you can pick out the titanium rod that we use for gas sampling, and each of these thermistor strings spans a thermal gradient. And then at our spring and stream sites, we deployed pressure, temperature, electrical conductivity probes in order to use a solute inventory method. And this requires developing some empirical relations between electrical conductivity and the concentration of some ionic species, and between pressure, depth, and flow rate, in order to arrive at a time series of solute flux. And this record is from Mount Baker, whereas this picture is of Mount St. Helens, with Kurt Spicer of USGS in the foreground. And this Mount Baker record shows that we can do a pretty good job of interpolating between site visits. These field measurements are pretty accurate. They're probably 10% or better, and they're very consistent with extrapolations from the probe. So now just a few selected results. This is just a record of some spring vent temperatures relative to adjacent ground and air temperatures. Nothing really new here, but it strikes me as remarkable, sort of counterintuitive, that the temperature of slightly thermal springs vents can stay constant, sometimes less than 0.1 degrees C variation in a year, while nearby ground temperatures vary by maybe 40 degrees C in the course of a year. If we ever do see temperature changes at these springs, it might represent a major shift in the system. Somewhat like Frederick Girault's observations in Nepal, these observations are still very rare. I don't necessarily think the events are that rare. It's just rare that we are making a record of them. And of course, we've looked at the sensitivity of all these data streams to seismic events. Chi Wang and Michael Manga at UC Berkeley suggested seismic energy density as a metric for evaluating hydrologic response to earthquakes. And that's an estimate of the total energy that a seismic wave train brings to a site. And it can be related to an earthquake distance, epicentral distance, and earthquake magnitude. And this line represents a seismic energy density of 0.001 joules per meters cubed. And seismic energy density increases in this direction on this plot. This value of 0.001 seems to be the approximate threshold value for a variety of hydrothermal responses to earthquakes. And the black and the red symbols are published hot spring and geyser responses to earthquakes. And by the way, the Tohoku earthquake 5 years ago generated seismic energy density of this magnitude throughout the Cascades. And at the time this figure was made, we had about 100 occurrences of seismic energy density greater than 0.001 joules per meters cubed. Really no clear-cut responses, just a few ambiguous ones. So a couple points are clear. These sites don't seem to be unusually sensitive to co-seismic strains. And second, our recording frequency, which again was generally hourly, is suboptimal for detecting seismic response, although hourly was all we could manage at first given probe limitations and our annual to biannual schedule of site visits. We could do better now, of course, because of improvements in instrumentation. But our thinking at the time was to at least have the temporal resolution to evaluate responses to earth tides and barometric effects and that sort of thing. So now we're going to look at some data from 3 of the 4 Cascade volcanoes that have had, that were active or exhibited unrest in the last 100 years. That's South Sister, Mount St. Helens, and Lassen. And we now have more than a decade's worth of probe data from South Sister. Remember, South Sister was sort of a prime motivation for starting this network, and this is our longest record by far. We didn't install probes at the other sites until 2009, 2010. But we don't see obvious trends here. The Mesa Creek record here, which is near the center of uplift, looks a little more variable after this break here, but actually we increased the recording frequency at this point, and the mean and standard deviation of data here and here really aren't that different. We have now have several more years of data from this site and still no obvious trends. And the helium isotope data composition hasn't really changed that much over the course of a decade either. This lack of obvious results is consistent with a hypothesis that the center of uplift is a locus of relatively frequent basaltic intrusion that rarely leads to eruption. It turns out this location is on strike with a chain of basalt cinder cones that extends about 100 kilometers to the north. And we think that this was sort of another failed eruption. Here's some of the record from Carbonate Springs at Mount St. Helens. Is really the only record other than Mount Baker, perhaps, that shows a pronounced secular trend. And this is one of our poorer instrumental records. It's plagued by biogenic fouling at this site, also, and seasonal vegetation growth that kind of disrupts the rating curve for stream flow. There are also, I put the elk in here because these are also a challenge. There's usually about a dozen of these creatures watching us work from this hill, and when we're done, they come down and try to disrupt our site, and they're quite strong. But over the multi-year period, both the instrument records and our on-site measurements tell the same story, and that's ongoing and fairly rapid decreases in temperature, chloride concentration, and chloride flux. Now, Devil's Kitchen is one of the main fumarolic areas at Lassen in Northern California, and heat and sulfate flux are the main parameters we measure there. It's an interesting site, partly because the first measurements were made in 1922, just a few years after the last eruption. Some of the findings here, there's about a 5-fold seasonal variation in heat loss. So if you're thinking about using Devil's Kitchen as an index site for Lassen, which is a natural choice in light of the long record, you need to take this into account. There's large variability that's not related to volcanic unrest. And second, if you monitor sulfate flux for a whole year, it becomes a pretty good proxy for the total heat loss from Devil's Kitchen. But on a shorter term, it doesn't work so well because lots of sulfur is stored locally at intermediate oxidation states. Pyrite, native sulfur are ubiquitous. But during the peak snowmelt, essentially all that sulfur oxidizes and is flushed out of the system as sulfate. And this accounts for these near zero late spring periods of sulfate flux. Essentially all the sulfur has been fluxed out. And then finally, it's not really obvious that there have been major changes in heat loss since 1922. The heat losses measured in 1922 were among the highest on record. I think they were these two here. But the record as a whole shows a strong correlation between stream flow and heat loss. And the 1922 measurements are within this envelope of recent hourly measurements, although barely. So, one of the challenging things about monitoring in the Cascades is the scarcity of actual eruptions. There's something like one every 50 years for the last 4,000 years. So the chances of capturing an eruption or even unrest during a 5-year experiment are fairly small. But we did see one unrest episode at Lassen in 2014-2015. And I've mentioned that with improvements in instrumentation, we are seeing more episodes of non-eruptive volcanic unrest, expressed, for instance, as low-level seismicity, ground deformation, and increased volcanic gas discharge. And it's useful to be able to diagnose and explain these episodes. And again, there was recent volcanic unrest at Lassen in Northern California. Lassen last erupted in 1914 to 1917, the second most recent eruption in the Cascades other than Mount St. Helens. And the Lassen actually hosts the largest and most visible hydrothermal system in the Cascades. It actually accounts for about 1/3 of the total high-temperature hot spring discharge in the Cascade range, in the entire U.S. part of the arc. And at Lassen, there are steam-fed features at higher elevations and liquid-fed thermal features at lower elevations, and they're connected to and fed by the same hydrothermal system at depth. These steam-fed features are acidic because of the CO2 and H2S that evolve with the steam, and they're associated with hydrothermal alteration products like kaolinite and alunite. And the liquid-fed features downslope are neutral pH, and they deposit silica. And around Veterans Day in 2014, there was an earthquake swarm south of the Lassen National Park boundary here on the Circle S Ranch, very near Morgan and Growler Hot Springs, which is our southernmost Cascades monitoring site. And this was the sort of swarm that David Shelley and his colleagues have mapped at a number of volcanoes. And this one was typical. It migrated generally upward at a rate of about 0.5 kilometer per day. And the largest event by far was this magnitude 3.8 on Veterans Day. And this is a, oops. Hey, it's working. This is an animation of the earthquake swarm, and it's courtesy of David Shelley, and this is a map view, and this is a cross section. And at the beginning of the animation, all the earthquake points are white, and then when the earthquakes happen, they show up as red, and the points then fade to cooler colors and then black with time. You'll see that progression on any of these points that it's not progressing very smoothly for some reason, but the size of the initial circle is proportional to the magnitude. And the magnitude 3.85 is about up here and should show up any moment. Or maybe not. But the magnitude 3.85 on Veterans Day was actually the largest earthquake within 30 kilometers of Lassen Peak in the last 60 years. And I didn't get up to Lassen until 4 days later. And this is one of our intermittent monitoring sites, so we didn't have instruments in place. And they were very happy to see me that day at Circle S Ranch. In fact, when I knocked on the door and said, hello, I'm from the USGS, they basically said, what took you so long? They live almost on top of that swarm, and they'd been feeling everything over about magnitude 1.8. In fact, they had the USGS website up continually, and they were, and every time they felt something, they'd check the website, and they were feeling dozens of earthquakes a day. And at the same time, they were seeing surging flow in the hot springs and new areas of steaming ground where they'd never seen steam before. So they were very aware at the moment of living on an active volcano. And they were happy to take me out to the hot springs to get water and gas samples. And then I went down to our usual monitoring site, which is about 5 kilometers downstream, to make a first chloride flux measurement and then to install an instrument to measure every 15 minutes. And although we didn't have an instrument in place, we did have the advantage of a long history of intermittent measurement here, and that proved helpful. This is the mean plus or minus standard deviation, these 3 lines, of 49 chloride flux measurements between 1983 and 2013. So what we saw in 2014 and early 2015 was very unusual, these pink measurements. And whereas the earthquake swarm only lasted about 10 days, the hydrothermal anomaly persisted for about 100 days. And it occurs to me I should say something more about the significance of chloride flux and why we choose to monitor it. In these young volcanic rocks of the Cascade Range, and I think this is more or less true worldwide, waters without any hydrothermal input have chloride concentrations that are near that of precipitation. Here, maybe 0.2, 0.3 milligrams per liter. The hot springs have concentrations of about 2,400 milligrams per liter, so it's a strong contrast. What's more, chloride is what we call conservative in solution. It stays in solution up to halite precipitation. So you can actually measure hot spring output quite accurately, and you could actually see this change in hot spring discharge about 80 kilometers downstream. In fact, every time Laura Clora and I went up to make one of these measurements, we did a repeat measurement 80 kilometers downstream, just kind of a double check. And we used a very simple model to simulate the hydrothermal anomaly, and that's one-dimensional flow between the steamy center of the system and the hot springs, governed by this standard set of geothermal reservoir engineering equations. And basically, you can match the observations very well by invoking a doubling of permeability quite close to the hot springs. There was a doubling of flow, so at some point you either got a double permeability or double the head gradient. So the permeability doubles here. This distance x1 controls the early time flow increase, which wasn't instantaneous, and this distance x2 controls the decay time. You can't make x2 very large without making the decay too slow. And the permeability increase apparently does not extend all the way to the hot spring vents, maybe because of the strengthening effects of near-surface cinder, which may be the most extensive cinder deposits in California. And let me just take a minute or two to describe these governing equations, because they'll come up again. This is our groundwater flow equation. It's maybe a bit unfamiliar looking here because it's written for multi-phase flow of fluids with variable properties. But we have to allow for variation in fluid properties like density and viscosity. So the equation is written in terms of pressure rather than hydraulic head, and intrinsic permeability rather than hydraulic conductivity. And then for generality, we allow for two different fluid phases, liquid water and steam. And we use this multi-phase form of Darcy's law, which includes these relative permeability terms. But basically, this equation just balances changes in mass stored with mass flux of liquid, mass flux of vapor, and any sources or sinks of mass. And the energy balance equation is going to be a little less familiar to most hydrogeologists, but it's analogous to the solute transport equation. It balances changes in the energy stored in the liquid phase and the vapor phase in the rock with heat advected by the liquid phase, heat advected by the vapor phase, and heat conducted, and then any sources or sinks of heat. And this equation is posed in terms of enthalpy rather than temperature, which is a convenient way of dealing with latent heat of vaporization. So that'll be the difference between the vapor enthalpy and the liquid enthalpy here. And it occurs to me, being here in France, that two of the fundamental empirical relations that are embedded in, that are the foundations of these equations were discovered here. Darcy's law, of course, in Dijon, and Fourier's law of heat conduction, maybe in Grenoble? I'm not sure, actually, but by Fourier. So, returning to the main thread here, is it reasonable to invoke a permeability increase in response to this level of seismic stimulus? That is the magnitude 3.85 event. And to make a long story short, we think yes, based on data from other sites such as Caltech's Pinyon Flat Observatory in the Coast Ranges and from other hydrothermal systems worldwide. The seismic energy density and the peak ground velocity are both seem to be in the right ballpark. And then one last point about this case study, these earthquakes themselves are probably driven by upflow of an endogenous water CO2 fluid, according to models developed by David Hill, David Shelley, others. Yet we haven't seen yet any signs of such fluid emerging at the vents, where we continue to find the vent fluid chemistry essentially unchanged. So where are we going from here? Well, the Cascade hydrothermal network, at least this iteration of it, it wasn't intended to be permanent. We're already scaling it back. It was intended as an experiment and also to collect baseline data about variability during quiescent periods and to provide context for key sites that could be reoccupied at the end of their useful lifetime. And it was intended, we're trying hard to archive these baseline data from the 25 sites in a useful and clear way. And Alana Crankshaw has been taking the lead on this. And for every site, Alana has correlated the primary variable monitored, chloride flux in this case, with the best predictor of that variable, which is stream flow in this case. And here stream flow explains less than 20% of the variance, so it's a poor predictor. these prediction bands in orange are basically plus or minus 2 standard deviations. So there's only about a 1% chance that a new observation would lie above this upper prediction band. And this example is the site that responded to the recent unrest at Lassen. The unrest really does pop out. For 100 days, the data are well above the upper prediction band, those red squares. And after that, they drop back within the prediction bands, those yellow squares sprinkled in there. So Alana's approach would have worked well there. And here's a few more examples from Alana. Chloride flux at Mount Baker, tightly predicted by stream flow. Single value from back in 1988 lies off trend. Perhaps this reflects the effects of the 1970s unrest. There's really no way to go back and figure that out. A highly predictive cooling trend at Mount St. Helens, which we've already discussed. This figure includes a few more years of data. Chloride flux on the west flank of South Sister, weakly predicted by time of year. And heat flux at Devil's Kitchen, highly predicted by stream flow. So we got relationships like this for all 25 of the sites. And these are basically one-page summaries of our results. And the idea is that 20 or 30 years from now, when one of these volcanoes gets restless, a future geologist could go back and make a measurement and see whether there's actually been a change or not. Anything lying above or even near this upper prediction band might prompt a more thorough look. And at the same time, we're scaling back our Cascades network. We're trying to scale up elsewhere. In particular, we're trying to refocus on places like Augustine in Alaska and Mammoth Mountain in California, where there seems to be a better probability of actually catching unrest cycles. And recent results from the literature do continue to suggest that hydrothermal monitoring can yield useful information. Recent eruptions at the Canary Islands and Mount Etna, where data sets are unusually good, were preceded by increases in the helium 3 to 4 ratios. These Ontake, Japan data are more typical, about a dozen measurements of helium 3 to 4 ratios over a 30-year period, but they still yield useful insight into the conditions that led to the disastrous 2014 eruption there. And it's not just helium. The CO2 to SO2 ratio changed before these recent eruptions in Costa Rica. So examples like these and our Lassen example encourage us to keep trying harder. And I mentioned previously that if we could choose a single hydrothermal parameter to sample continuously, it would be the helium 3 to helium isotope ratio, but we don't yet have the technology to do that, so we've been relying on proxies. And seeking a more direct approach, we've been doing some experiments with passive diffusion samplers for gas composition. This is a collaboration with the University of Utah Noble Gas Lab and the Geological Survey of Japan. The GSJ recently deployed 10 of these prototype samplers on Izo Oshima volcano. And the next 3 slides I'll show are from Brittany Dame's MS thesis at the University of Utah. So again, this problem, we've got seismic unrest at a volcano. We'd like to know gas composition and whether and when it changed. But of course, in practice, we might not even have this before sample. So what if instead we installed a sampling array in advance that passively records and updates gas composition? That's the idea here. These samplers are identical except for the size of the gas reservoir, small, medium, large, and gas diffuses into the samplers through these membranes, and because of the differences in reservoir volume, the equilibration times are going to be different. Equilibration is a diffusive process. It's governed by the diffusion equation. So the inverse problem is going to be similar to somebody inverting, a groundwater person inverting hydraulic head for permeability, or somebody inverting gravity for density. you can't really back out a detailed time history, but Britt experimented with two models, this one-step model here and then a two-step model where concentration goes back down. And this approach, we think, does show some promise, and we documented the method in the Bulletin of Volcanology last year. And then finally, our newest work, still in progress, but we're quite excited by it, and this is a collaboration I've been able to continue here in the last week or so. And this work's inspired by a recent JVGR paper by our colleagues Randy White and Wendy McCausland. And it's a collaboration with the ENS student and colleague Cecile Cologne. In fact, Cecile is Sophie Violette's student and at ENS, and she was just on loan from them to USGS for about 5 months. Now, this problem, precursory distal volcano tectonic seismicity. Our volcano disaster assistance program has found that this sort of seismicity seems to precede all explosive eruptions of a certain magnitude in their data set. And the thing that makes this, I think, fairly profound and interesting is they have about 110 examples. And this distal seismicity is seismicity off on the flanks of the volcano at a mean distance of something like 6 kilometers. It's not centrally located, and it precedes the more central seismicity that is often more or less coincident in time with the eruption. And the mean intrusion, these are usually fairly small intrusions, fairly small eruptions. So Randy and Wendy developed this hypothesis that this so-called DVT seismicity occurs when aquifers are overpressurized by the intrusion of magma, and each pulse of intruding magma transmits pressure through the aquifers that intersect tectonically pre-stressed faults. And this colleague of mine, Randy White, has actually been the seismologist at 80 eruptions. He's been sort of the attending seismologist at 80 eruptions. So that's the basis for his strong feeling that this is the case. And so what we're basically trying to do is explore this hypothesis quantitatively. We're trying to figure out why a small central intrusion would cause distal pressure changes about 70 days before significant near-vent pressure changes occur. And we're using the same set of governing equations that I described previously, and Cecile's exploring, and Cologne is taking lead on the modeling along with our colleague Paul Shea. And the key governing parameter is almost certainly going to be permeability, and Cecile's exploring a range of permeabilities from values low enough that heat transfer is conduction dominated to values as high as the most permeable geothermal reservoirs. And she's looking at anisotropies ranging from essentially none to a factor of 10 to the 4, which would be a value appropriate to, say, continental flood basalts or something highly anisotropic. And in this top case, the intrusion is bringing actually in this whole slide, the intrusion is bringing heat with it only, so no devolatilization, just heat. And if the flow is channelized, things look pretty good. The sweet spot for timing is more or less this teal color. The sweet spot for magnitude of pressure change is more or less this red color. But volcanoes have nominally radial symmetry. For the equivalent case in radial coordinates, pressure dissipates much more rapidly with distance, and the sweet spots shrink or even disappear. And then here, Cecile allows the intrusion to bring in a reasonable amount of volatiles in addition to heat, and the sweet spots expand again. And this is sort of her best match. And I like it because the values of permeability are sort of in the range of 10 to the minus. Well, they're more or less in the range of productive geothermal reservoirs. So we know such permeabilities exist in volcanic terrain. And the anisotropies are a factor of 10 to 100. And we know that those sort of anisotropies are typical of volcanic terrain as well. So that's it. I'm looking forward to answering questions. We also have some related publications if you want to, anybody wants to dig into this in more detail. This is the heat discharge inventory that we did during planning stages. This is the where you can find the hydrothermal monitoring data online. If you Google hydrothermal monitoring, this is the first thing that comes up, and you can find all our data there. We're always hoping that somebody will pick it up and do something smarter with it than we've been able to do. This is the first description of the monitoring network, and this is the these are 2 recent papers on Lassen. So that's it. Thank you very much for your attention. I hope there's some time for questions.
I think I was particularly taken by, the relationship that you showed only very briefly between INSAR data and hydrothermal, events and so on. Now, is that something that in the U.S. we're somewhat handicapped with by not having, our own constellation of satellites that we can routinely monitor these things much more often?
The absence of, you're referring to the absence of U.S. INSAR. Yeah, right. Well, I think that our INSAR folks do have access through cooperative agreements to data from the Japanese and European satellites, I believe it is, that are kind of the core capability. I mean, there is a plan to have NASA have something up there in 2020, that. There's also some interesting things happening at the Stanford Research Institute, which is immediately adjacent to our facility. They're looking at drone-mounted INSAR now. So that could solve the frequency issue for particular locations, I suppose. And of course, a lot of these U.S. volcanoes, at least, continuous GPS gives you somewhat of the continuity between INSAR images for at least a few points.
Yeah, yeah. You have a number of these thermal records of temperature versus time, and you see some relaxation. What are we learning from the relaxation time from what's going on inside?
From the thermal relaxation time. Well, are you thinking of a particular example, or are you thinking of...
You had a few of these slides where you see this is going up and then it's going down again, kind of an exponential way. What are we learning from this
the most
time here?
The most pronounced long-term trend in our data set is Mount St. Helens, I think. It shows a strong seasonal superimposed on a steep decline. And I think that what that's telling us is that heat source is fairly local and shallow.
You had non-seasonal variation at some point. One of your early slides. Don't you remember? You had these things going up and down exponentially a couple of times. You had peaks and then relaxing.
Is that maybe that was the Devil's Kitchen example where you had repeated? Not
on a seasonal base.
Maybe we can talk more about that afterwards, because I'm not thinking of the particular example that you're... We can find it, but I'm...
Qui veut poser des questions? Personne? So, what is the source of the chloride that you see associated to helium-3? it's mantle chloride, or it's going from chloride which has been stored in the soil somewhere and is remobilized during the influx of fluids?
That's an argument that's been around for almost 100 years in these environments, and I'm trying. I hear the geochemists argue about it, and I try not to take a strong stance because I'm not enough of a chemist. But to me, the fact that in the South Sister area we have such a strong correlation between helium-3, heat, and chloride, to me it tends to argue for a magmatic source. But that's true. You can hide a lot in a log-log plot, can't you? A lot of variability.
Okay. And then also, the correlations are nice, but then the question is, of course, to set the threshold to say that something is going to happen. And in fact, this is not so clear to me. And even if after that, the links between unrest and volcanic activity is completely unclear also.
Right. And that's, I would say that at the USGS, our colleagues have followed geodetic and seismic signals through 100+ eruptions. Mm-hmm. So you have a sense of what means what, and you can use analogy from event to event to make forecasts. And we have very little experience with this kind of data. We have not traced it through many eruption cycles. So I think we're at a point where we need to think strategically about what do we measure where. I mean, we have 170 active volcanoes, and most of them are very remote, such that keeping instruments going year-round and telemetering data is a huge challenge. So we need to think, what are the next steps after we've done this experiment in the Cascades where things are fairly easy.
Tintin.
So I anticipate that the USGS is working very closely with the New Zealanders, with the Japanese, and are there strong differences in the styles of hydrothermal activity between what you see in the Cascades and what you see in Taupo or parts of Japan chain?
Well, as I said earlier on, the hydrothermal activity in general is much more vigorous in both those places. I personally have been working a lot with Japanese colleagues in the last couple of years in relation to the Antaki eruption. And do you guys remember that one? It was about 2.5 years ago. It killed 62 hikers. An eruption went off with really no warning, and the Japanese have been working hard on trying to figure out what happened and how to avoid it happening again. Well, maybe this is more of a digression than a full answer to your question, but it's kind of an interesting one. That Antaki has actually had 5 purely hydrothermal eruptions since 1979. It's sort of cyclic. The last one before this one was even larger, but it occurred at a time of day and a time of year where there was nobody on the summit. But what they think is happening there is that the hydrothermal system is pressurizing, blowing itself open. That's basically these eruptions, and then gradually resealing due to water-rock interaction. And when it reseals, the fumaroles stop flowing, and one would think, oh, the volcano is getting quiet, but really it's not. Pressure's building up under the seal, and it's just in a preparation phase for another of these sort of cyclic hydrothermal eruptions. So they're trying to get more and more continuous temperature, gas chemistry, and they're also continuously monitoring near summit magnetic fields, because they think they can see this heating phase, the sealed heating phase, as a demagnetization. And they also have that same model for Tokochidaki volcano up in Hokkaido, which is the most disastrous eruption before Ontake, also purely phreatic, and it killed about 120 people in 1924. It also seems to have this episodic pressurization of the hydrothermal system, blowing itself open, sealing itself up, and so on. In New Zealand, we have been in contact. New Zealand is kind of using what we've done in the Cascades as a bit of a model for their first efforts to do continuous modeling. I think they're monitoring. I think they're talking about a half dozen sites, and we have been in contact, and of course I hope they'll do better than we did. Think of things to do that we didn't do.
I guess my question was one of the science of it, whether you see the same correlations, for example, with chloride and helium and these other systems.
Yeah, that particular data set is the best I know of from that regard. That we really went at that site pretty heavily because we were so excited about that bulge at the time. But those helium, every helium isotope analysis is fairly expensive. So we're going to put a continuous mini mass spec out on Mammoth Mountain in the next year or so. So that'll be to look at helium ratios.
Okay, last one.
I have. I'm just wondering. You didn't mention anything about volcanoes such as Hawaii or Reunion Island, and because I was wondering whether the observation would be similar or not, and whether they could be used as a way to find why there are correlation and when and how and so on, because it's more continuous. I'm just wondering.
That's a great. I really don't know what you have on Reunion Island. There is one deep drill hole on Kilauea Summit that has tantalized us for years, but the water chemistry and the temperature are so aggressive that we've never been able to get instruments to live very long there. Our program on it's about a kilometer deep drill hole right west of Halemaumau, if you know Kilauea. And for a while we had quarterly kind of bailing sampling going on, but every effort we made to continuously monitor in that hole so far has been unsuccessful. Or we get brief, we may get 30 days of record. We really want to have years.
Okay. So, thank you. Thank you again. On peut continuer la discussion à la médiathèque où il y a un buffet qui vous attend. Voilà, vous serez plus libre pour parler.